So one of the last remaining topics regarding functions of several variables that we have to, or at least differentiation of functions of several variables that we have to discuss, is the multivariable chain rule. Again, it's not that different from the ordinary chain rule that you know from Calc 1. There are just more possibilities that go into consideration. Really, you could use like Taylor's theorem to approximation to sort of try to derive the formula. If we knew more linear algebra, I could try to do like a more interesting explanation for why this is true, but for now I'll just do like an analogy. Hopefully it will be convincing to most of you. But if you look at say a function of x, well, I think I was going to use the exponential function. Let's say e to the x, but then x is at the same time a function of t, like say t squared, right? Then you can regard f as a function of t, which is e to the t squared, right? And then you would say, well, the f dt, what you learn from the chain rule is the same as the f dx, the x dt, the f dx, that's just e to the x, the x dt is just 2t, right? And then you can choose to, I mean, if you want to see everything in terms of t, you can just substitute x with the expression in terms of t, and you get 2t e to the t squared, right? Which, again, the chain rule takes a while to understand, but once you get used to it, it becomes very intuitive. Now, one way to think about this is more diagrammatically, meaning let's put at the top level a function that we care about. So that by that I just mean the function f. I'm saying that the immediate dependence of f on a variable is on the variable x, and then the variable x at the same time depends on t. Okay? So when you go from the top level to the one in the middle, when you lower a level, you'll take a derivative. We're just relating the derivative. The numerator is the one the top level, the denominator is the one in the middle. And then when you go from the middle to the bottom, you'll also take some derivative. And now the numerator is the one in the middle, and the denominator is the one in the bottom. Okay? And so really what the chain rule is saying that, well, not that we recommend this. Like if you were jumping, if you think of them as different levels on a building, if you want to jump from level 2 to level 0, you can jump from level 2 to level 1, and then from level 1 to level 0, or you can just jump directly from 2 to 0, which is doing this. And so if you think about it, the chain rule is just saying that jumping from 2 to 0 is the same as jumping from 2 to 1 and then from 1 to 0. Now let's think about what happens in the case of, say, two variables. The point is that a similar diagram works. So say now the function is e to the x sine of y, and then x is a function of t and s, like t squared plus s, and y is a function of t and s. I guess ts could be interesting. Okay? And so, again, that means that secretly you can regard f as a function of t and s, right? If you want, you can say that this is e to the t squared plus s and sine of ts. And so from that point of view, once you know explicitly f as a function of t and s, you could compute all the partial derivatives that you want in the world without problem, right? Now the point is that in general, this is similar to why we have product rules for cross product. Why is that useful to have, even if in practice you could always do the substitution or differentiate, do the cross product first and then differentiate. The thing is, like, in some cases you don't know the concrete formulas for the functions, so it's still useful to know that there's like a chain rule that works, even though you may not know all the specifics about the functions that you care about. So for example here, if you wanted to, if you cheat and do the substitution, then you would say, oh, the partial derivative of f, say, with respect to s, just to make one easy. Well, let's do both. The partial derivative of f with respect to t would be a product rule first. So is the derivative of this one. And then by the chain rule, you have to multiply by the derivative of this with respect to t, which is 2t, times the second one, plus this one without differentiating, times the derivative of the second one, which is cosine of ts times s. Okay? And likewise, you could do the derivative of f with respect to s, which would be the derivative of the first one. Now the chain rule just gives you 1, so you don't have to worry about anything, times sine of ts, and then you just differentiate the second term. So this gives you cosine of ts times t now. Now I'll explain to you how to find this from this perspective from the diagram. So sometimes these are known as tree diagrams, or just like a multivariable chain rule, but it's the same principle as the one that was happening here. So f a priori depends on two variables. The immediate dependence of f is on the variables x and y, but then the secondary dependence is on the variables t and s, just because each of these depend on t and s. So here we put ts, ts. Okay? And so, for example, every time, so you have all these possibilities, and every time you lower a level, you have to take a partial derivative. So for example, here it will be the partial derivative of f with respect to x. Here's the partial derivative of f with respect to y. And here's a partial derivative of x with respect to t. Partial derivative of x with respect to s. Partial derivative of y with respect to t. Partial derivative of y with respect to s. Okay? And so, if you say are interested in the first partial derivative, the one of the partial derivative of f with respect to s, then that means that we have to travel you need to look at all the possible ways that you can start at f and end up at s. So one possibility is to go this way and then this way, or you could go this way and then this way. Okay, and so in essence, what you do is for each possible path, when you lower levels, you multiply, and when you switch to another branch, you just add the contributions. Meaning that here, if you start with the first path, you do partial of f with respect to x, and then partial of x with respect to s. And then when you switch branches, do another contribution, you do now partial of f with respect to y, and then partial of y with respect to s. And then you're good to go. Partial of f with respect to x, that's e to the x sine of y. And then partial of x with respect to s is just 1. And here you get partial of f with respect to y, which is e to the x cosine of y. And partial of y with respect to s is just t. And you do the substitutions, right? You substitute x with t squared plus s here, and y with ts, and you can notice that this is exactly this one that you saw here, right? And something similar, I mean, it's the same, I would make the substitution, but I'm running out of space, and I do want to make the other one here so that you can compare it. And so, for example, if you wanted the partial derivative of f with respect to t, again, you just ask how many ways do you have from going from f to t. You can go here, and then here and here. So that gives you two paths, and again, it's just the same story, partial of f with respect to x times partial of x with respect to t now, plus partial of f with respect to y times partial of y with respect to t. Notice, before I forget to mention this, that if you were completely computer type formalism person, like you would say, oh, like symbolically it looks like almost as if you're canceling this with this, this with this, and it almost gives you what you want. It just seems to give you twice the partial derivative of f with respect to s. So that means that the notation is almost perfect. You just have to be a bit more careful with what's going on. So you cannot just do cancellations like crazy, and that will become more clear in the next video. But it almost is as good as you might expect. Now this we already computed before. Partial of x with respect to t is 2t. Partial of f with respect to y we computed before. And the last one, partial of y with respect to t, is s. And so you see, you get precisely, after you substitute x and y in terms of t and s, you get precisely this term. Okay, so the diagrams are very intuitive, and you just have to look at all the possible paths that connect the original function with the desired partial derivative that you want to compute, and then you just add all the contributions.